Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel about everything I want to talk about, science and math. And today we are in chemistry, talking about equilibrium, percent composition, and empirical formula. I don't know if we'll get it all, but we're going to at least start it here in part one. All right. Okay, how do reactions occur? What do the atoms have to do to be able to react with each other? What? They got to come together. Perfect. They have to collide. So, am I on draw? It's all about collision. This is called collision theory. So we have to have them collide. They have to come together to react. So we have to have collision theory. Now, there are certain factors that affect reaction rate. And we are going to do some fun little labs to help imprint this into your memory. Okay, so the first thing, say I've got a reaction and I want it to go faster. What can I do to make it go faster? Heat it up, always. We can increase the heat. This increases the atom's speed so that they collide faster. Also, the activation energy may be supplied. So, we've talked about this before. Here I've got a box of matches. If they react, they're going to combine with the oxygen in the room. I've got matches, I've got oxygen. Why are the matches not catching on fire? They need some energy, they need some friction, and they also need the other chemical that's on the strip. But even if I take the match and hold this chemical to that one, they are not reacting. And the oxygen's here in the room, but it's not reacting because it needs the friction to apply extra energy to make it go. Now, do you think if I started heating this up, it might go? Probably so. And boxes they used to have strike anywhere matches. I think they still do. But people would leave them in their car. They would heat up and catch on fire. People would go out to their car and it would be burnt up, especially here in the South where we have really hot summers. Okay, what else could we do? So, like, you got a fire, you want it to go better, and you got some gasoline. What do you think you might do to it? Pour a little more on it, add more. So adding more, have you ever tried that to get a reaction to go better? Let's add some more and see if that helps. So that's increasing concentration. Do you remember the symbol for concentration that I told you? It's square brackets. So I'll draw some little square brackets, and it's concentration. More particles, more chance of collision, more likely that we're going to have a chemical reaction. What else could we do? We could put them in a smaller area. We could squish them together. So we could increase the pressure. Y'all know the symbol for pressure? Capital P. But we'll go ahead and write it out. Increase the pressure. Squish them together. More chances of a collision. What else? Is it easier to burn little matches or a great big Yule log for Christmas? The smaller matches, right? It's very, very difficult. If you have a fireplace at your house and you have a log that's not split, it is hard to get that log to burn. If you split it, if you make it smaller, it's much easier. So what is happening if you have smaller particles, and this is a weird one, so everybody think hard about it. If you have smaller particles, you increase the surface area per volume. So the smaller something is, the more surface area it has for how big it is. You can think about this with dogs, okay? You see a little Chihuahua dog. It's the wintertime and it's cold. That little Chihuahua dog will start shivering, won't it? But if you have a giant Great Dane, even if it's cold, do they shiver? No, because for their size, for its volume, the Chihuahua has much more skin per dog. Yes, it has less skin overall, but for its volume, it's got more skin, more places for the heat to be released. The great big dog doesn't have so much skin per its volume, so it's not losing its heat and it's not getting cold. Does that make sense to you? Can you sort of imagine it? You kind of know it already, because which one dissolves faster? A cube of sugar or like that powdered sugar that comes in the little Kool-Aid things? The powdered. Why? Greater surface area. So, surface area. The smaller particles have greater surface area to volume ratio and react faster. And then I have here exploding grain solids. Okay, Thanksgiving's coming up. Anybody ever worry about your ear of corn on the cob blowing up and blowing your head off in the middle of Thanksgiving? No. But corn explosions kill people every year. But you just eat that corn not even thinking about it. And it's because we live in the Southeast. Out west, they understand this more. People who are more from the west, where they grow grain. If you go and you've got your corn to turn in to, because you're selling it, you're turning it in for to be ground, whatever, and you go there to these places with your crop, there are signs all over the gates. No sparking, no smoking, turn off engine immediately as soon as you can, because there they have corn and other grains that have been ground into fine dust. So it's got it's very small particles, very high surface area, and if there's any kind of spark, it'll explode. Grain silos will explode, and farmers are killed every year by exploding corn. Is that just crazy to you? My old chemistry professor at Georgia State was from out west. He always wore the Western shirts, with the buttons and the stitching every day. When he wasn't in class, he had his cowboy hat on. He was a cowboy, and he knew people who had died from exploding corn. So it was very serious to him. And it's this: the greater the surface area, the reaction is faster, even an explosion. And then the last thing is the chemical nature. The chemical nature. Some things are just more reactive than others. One of the big problems we had at school last year until over this summer is there were chemicals in the back that what happened was when everybody got sent home for COVID, they just left on that Friday and didn't know they weren't coming back on Monday and were going to be gone for months. So there were things in that stockroom in my chemical stockroom, that it wasn't me, it was a different teacher, but there were things that were not secured as much as they should have been. There were some very reactive chemicals, and there they sat all summer reacting. And when I came in that next fall, I was like, oh no. There was a haze of chemicals in the air where things had reacted all summer and it was then airborne. We pretty much have gotten it all gone now. Every now and then I see little traces of, oh, that was from the big reaction. So I think I figured out what it was that reacted, and then it was some things with some halogens in them. Halogens are very reactive. They want to be noble gases. They're only one away. They're ready to react. All right, so sometimes the reactions need, and we already talked about it, a little bit of energy. It's called activation energy. Big E is the symbol for energy, so you need to memorize it. They need activation energy. Now this graph, I'm going to roll this up. Hold on. This graph is a classic graph. Every chemistry student ends up learning it, and you always have to label it. It's just a rite of passage. You got to learn the activation energy graph. So the energy is on the side. It's called Gibbs free energy, but you don't have to care about that. It's just energy. The reaction progress is on the bottom. You start off with your reactants at one level of energy. After the reaction, it is less energy. It's more stable once it's products. But for it to go from reactants to products, sometimes you have to get over a little energy hill, like our match. This is the energy of activation, symbolized E sub A. The difference is the energy difference between the reactants and the products. Any questions about that graph? Does that make sense to you? Think you could label it? You know what it is? That's the activation energy. And then, see, once you get over the activation energy, then the reaction just goes by itself. My match, once I light it, I don't have to keep rubbing it on the box. It's ready to just keep going. Good? All right, the next thing is sometimes you can speed up a reaction with a catalyst. A catalyst, and we talked about that. It's like a matchmaker. It puts the chemicals together so they can react. An example you learned last year in biology is the enzymes in your body. They are made of proteins. Remember that from honors biology? Made of proteins. And notice that this increases reaction. The symbol for reaction is RXN, rate. So it increases the reaction rate to add a catalyst. It's going to react faster. Any questions about page 1? Let's roll on up then. The catalyst is a matchmaker. It doesn't actually take place in the reaction, but it speeds it up. Can I roll all the way up? Nope, I can see people still writing. Now, can I go? Okay, we're going. Composition. So look at our standard. We have learned everything for standard 3 except percent composition and empirical molecular formula. So this standard, this test is going to finish this standard, those 2 things, and then we're going also onto the other concepts in the next standard, which are all on the back of your thing. All right. Sometimes it is useful in chemistry to know the composition in terms of mass or weight. We still use weight and English measurements a lot in the mining industry. So, example, you found some copper. Is it enough copper in the ore that you found for it to be worth it for you to mine it? Just because you found copper doesn't mean that it's enough that it might cost you too much to build a mine, to get the equipment, to hire the men, to pay for health care, and women. I guess there's women miners. But, that might cost too much. You might not make a profit. Now, if it was gold, you might be right on it. But copper, you need to know. Do a little research. Okay? So, is it worth it to mine this copper that you found? Okay? So, here is an example problem. So, Carvoni, I'm sure I'm saying that right, C10H14O causes the smell of spearmint. We made some of these smells. This is not one we made, but it's spearmint oil. We want to calculate the percent composition in this. So, this is how you do it. You will be given an element. You list it. I want you to do it exactly like this, just like how you do with the stoichiometry. If you do it exactly my way, it'll make sense. I want you to list your elements horizontally. Then I want you to look at the subscripts and tell me how many you have. So I have 10 carbons, 14 hydrogens, and 1 oxygen. Then I look up the molar mass of each one. So this is just like what we did in the last problem. And I multiply them out, and I get 120, 14, and 16. You add them up, and it's 150 is our total molar mass. So all this is, everybody put a little M&M there. That's just our regular molar mass that you did for the last test. Okay, but then what you do is you take the molar mass of each part, and we're going to divide it by the total, and that's going to give us the percent of each part. So my first one is copper, and it's 120. I write it right here. I divide it by the whole thing, 150, and I get the percent of carbon in this is 80%. I do the same thing with the hydrogen. It's 14 out of 150. I multiply it, and I get that it's 9.3%. And then I do it with the oxygen. It's 16 divided by 150. Multiply it out, and it's 10.6%. Now, one thing you can do to check it is to add them up, and they should equal 100. So that's your little check. Is the answer to this problem 100? No. The answer to this problem is it's 80% carbon, 9.3% hydrogen, and 10.6% oxygen. So I'm going to put that in a box. That's my answer. Make my box bigger. All right, how do you feel about that problem? Is that easier than stoichiometry? Yes, Jesse. What? 120 divided by 150 is 80. 14 divided by 150 is 9.3. 16 divided by 150 is 10.6. All right, that's a good stopping place. Wait, let's see if we got a question. Got it? He's good. All right. Like, share, subscribe. Science is great.